All right. Today we're going to be talking about variance and standard deviation. This will be Unit 20.6a notes. We'll do 20.6b tomorrow. We're going to be talking about variance and standard deviation, which are very important when you want to start talking about the spread of data. You know, because the range and the IQR, they only use two values in their calculation. And, you know, as we've seen, just having range and IQR can actually hide a lot of characteristics of a data set's spread. So we need more than just IQR and range to talk about spread. So let's consider a set of data points, x1, x2, yada, 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 out to xn, with mean being x bar. What we're going to say is that xi, meaning some generic term in the list, minus x bar. So what we're talking about is the distance between any term in the list and the mean is going to show you how far an individual term deviates from the mean. This measures how far any generic term x sub I deviates from the mean. And we use this to find the variance of data. The variance of a sample of n data values is not a pretty formula. You don't have to have the formula memorized, but there is one really important part of it, which I'll just show you in just a second. So here is the formula. You don't need to have it memorized, but it says S sub n squared. So this means the variance of n data points, or the standard deviation of n data points squared. So this S sub n is how we say the standard deviation. Squaring it gives us the variance. It's found by adding up all of the squares of the xi minus x bars, and then dividing whatever that number is by n. So you might be wondering why squared. The reason why it's squared is because that will guarantee that all of our numbers are positive now. So if you want to talk about the variance, it's almost like the average of the average distances from mean, if you want to think of it like that, because you are dividing by the number of terms. So yeah, xi minus x bar is squared. That way we know that everything is positive. Now if the distance is squared and then summed up is small, so if that sum is small, this tells us that most of the data values are actually close to x bar. So that would mean that we kind of have tightly packed data clumped around its mean. Now, unfortunately, the variance itself doesn't really tell us much about the spread of the data. Instead, it's more like if you knew the variance of two different sets, then you could say, okay, well, since that one's variance is smaller, we know that it's tighter packed data. But what represents a large variance or a small variance is not really something that we measure. So basically, it's only used for comparing to other data sets. This one has a greater variance, so its data is more spread out than another set's. However, if you were to square root your variance, you would have S sub n. And S sub n is called the standard deviation. So what we would have is S sub n equal to, and it's legitimately this formula up here with a big old square root bar over it. And that is called the standard deviation, like I said. So what are some important things to know about the standard deviation? Well, the standard deviation is a non-resistant measure of spread. And that means that it's actually pretty easy to mess with simply by adding or removing data points from a set, especially if they're far away from the mean. So we say that it is a non-resistant measure of spread. And that's because it is dependent upon the mean, which can be affected by extreme values. Let's see if I can squeeze dependent in here. Yeah. Is it affected? Affected? I have A on my paper. I don't teach English. I just hear my phone. I'm getting a lot of text messages next to me. So when is standard deviation useful? Well, it's actually only useful if a distribution is relatively symmetric. So it's only useful if a distribution is relatively symmetric. Does that mean that we don't have standard deviations for data that is not symmetric? No, those do exist. There's outside the realm of what this course covers. I think it's called Chevyshev's measurement or something like that. I'm pretty sure Chevyshev is the name. There are ways of calculating standard deviations of non-symmetric data. I don't really know what it's used for because I'm a mathematician, not a magician, but I know it exists. Now, standard deviation is especially useful if the data is, wait for it, symmetric, right? Normally distributed. So, what color do I want to use? Blue. Blue feels good. Especially useful if data is normally distributed. That means fits a bell curve very well, which is symmetric. And the last most important point about standard deviation that you need to know is that most of your data points are going to fall between the mean plus or minus 1 standard deviation. It's actually roughly 68% of your data points. You don't need to know that yet. I'm just letting you know. Most of the data points should fall between mean plus or minus 1 standard deviation. Okay. Just have the one example to finish up these notes. Survey was done at a local library over a 5-day period where patrons were asked whether or not they were satisfied with the books they checked out. The survey was repeated a couple months later after an overhaul of the selection of books. The survey results are in the tables below. So survey 1, we see that we have 1, 2, 3, 4, 5 days, and this is the number of dissatisfied people across the 5 days. Let's go ahead and fill out what we need in order to tackle all this stuff. I mean, we're not going to be able to find the standard deviation without the mean, and we can't find the mean without knowing the total number of things. And then once we've got the two tables filled out, we can compare them, and then we can tell us, what do these statistics actually mean to us? All right, let's see. Good colors. I'll go back to blue. I like blue. 3 plus 7, 6, 8, 11. Quick maths. That is 35 unhappy people. Well, A says find the mean. Okay, well, X bar is going to be our 35 unhappy people that we found across those 5 days. So we are getting an average of 7 unhappy people per day. So then what you're going to do in this column is you're going to take this number, this is xi, and you're going to subtract the mean. So here we have 3 minus 7, 7 minus 7, 6 minus 7, 8 minus 7, and 11 minus 7. For the final column in this table, we square all those values, ensuring that we get positive numbers. 16, 0, 1, 1, 16. And then we add xi minus x bar squared, because we need, if the formula has a sigma in it, so we have to add all these up. This gives us 34. Awesome. Now we're going to do the same thing for the other table. And once we've got the other table completely filled out, we'll go back and we'll figure out the standard deviations for both things. Other table, use purple. Okay, 2, 3, 5, and 10. That is 20 unhappy customers. So our X bar here is now 20 people across the 5 days, which is only 4 unhappy customers per day. I mean, you can see on average, the new books are better, right? But there's more to data than just average. 2 minus 4, negative 2. 3 minus 4, negative 1. 5 minus 4, 1. 4 minus 4, 0. 6 minus 4, 2. Square all those values. 4, 1, 1, 0, 4. And that adds to 10. Let's track down our standard deviations. S sub n is the square root of, we have sigma x minus x bar squared, and we're going to divide that by n. So for part A, our standard deviation is 34 over 5, and then the square root of that. And if you don't know what that is right off the top of your head, you're probably in the wrong math class. Jokes, I'm kidding. I have no clue what that is. Without a calculator, of course. The square root of 34 divided by 5 is roughly 2.61. Okay. Grab good old purple pen and do the same thing here. This standard deviation is the square root of 10 over 5. Whoa. That's the square root of 2. You might actually know that one roughly. About 1.41. So part A is finished. We have found the mean and standard deviation of each survey. What do these statistics tell us? Okay, we're going to write a lot here. What do these statistics tell us? Let's see if I can get it all to fit on the screen here. Write in red. B. The X bars show us that the number of dissatisfied people is almost half of what it used to be. How do you spell this word? Nearly half what it used to be. Now, what about these standard deviations? Well, the smaller standard deviation tells us that there's less variability in the number of dissatisfied people. So it's almost like the vaccination box and whisker plots that we were looking at, where we had the tight box told us that that was a more predictable medicine. This is the same idea. A smaller standard deviation says that there's less variability in the study. So that actually means that the number of dissatisfied people is going to be closer to the mean than it used to be. That's what a smaller standard deviation tells us. And as long as you're comfortable with all that, you at least have a cursory understanding of variance and standard deviation. and that will finish part A for us.